So I will speak basically about numerical evaluation of elliptic multiple polylogarithms within GiNaC. So basically there will be three parts. First, how multiple polylogarithms, the non-elliptic versions, are handled in GiNaC.
Stefan, there is Matthias on the screen. On your screen, could you move him?
Okay, I move him basically.
Yeah, that's perfect.
I think I move him to this corner here.
Yeah, thanks.
Maybe. Okay. I think that's okay. Second part will be basically the background, about elliptic curves and functions associated to them. And the third part, then basically what we will do in GiNaC. This is work done with Moritz Walden and based on previous work with various collaborators. Maybe let me remind you that in the end, physics is always about numbers. As a mathematical physicist, of course, a symbol like θ3 is very aesthetic, but as soon as you start to talk to an experimental physicist, he really would like to have a number like this one here. Now, in the title of the talk, there's GiNaC. So GiNaC basically was initiated in 1999 by three persons from our university. And despite its name, it's actually a computer algebra system, and it allows you to do symbolic calculations within C++. It's a library for C++ for symbolic calculations. Now, basically, it comes with all major Linux distributions, which makes it very easy to install. And if you really want the latest version, of course, you can download the source code at this web page here. Part of GiNaC is basically a subpackage, which can be used to evaluate multiple polylogarithms with arbitrary precision. That already exists for a while. And okay, I don't have to remind you basically here what multiple polylogarithms are, but nevertheless, I would like to give the definition here. There are two versions how you can define multiple polylogarithms. First, through an iterated integral, defined in that way. And here I assume that basically the last parameter, set k, is not equal to 0. Or alternatively, based on a nested sum, then we use the notation li, and basically it's defined like here. Both definitions basically define the same class of functions, and there's a relation between them. If you basically first introduce this shorthand notation, if you have a bunch of zeros before any non-zero element here, and then the relation is given by this formula there. So basically you can pick the notation which suits you most. And there's even one thing which we can do, and which we actually do, is basically to enlarge this definition slightly a little bit to allow trailing zeros. So basically I said here before, in order to make that sense, that you can integrate down to 0 here, this set k should be not equal to 0. Now, if in the string you have in the end some zeros, you just define it by this formula there, and then you can define multiple polylogarithms with trailing zeros recursively through that formula here. I believe that is well known. Now, these things can be evaluated numerically, and in GiNaC, it also offers a small shell where you can type in some simple commands. And if you say, okay, I want 50 digits, and then you just type in this line here, you get multiple polylogarithms of weight 3, which in that case is minus θ3, and you get the first 50 digits of that number. And then you can put in any number of digits you want. You may ask, why actually do I want 50 digits? If in the end, it goes to experimentalists, they can, if they are good, measure 8 digits maybe. Usually it's just 5 or something like that. So why 50? There's a reason for that, And the reason is we not only in the end would like to provide numbers to experimentalize, but we also, when we work out new Feynman integrals, we sometimes need boundary constants. And there's a very smart algorithm, the PSLQ algorithm, which can be used to find integer relations among a set of transcendental numbers. The condition to use this algorithm is basically that you know the transcendental numbers to sufficient high precision, meaning with sufficient number of digits. And basically theta 3 or the Li 4 of 1/2, they are of course transcendental numbers and they occur as boundary constants, and you can use to fix and to simplify boundary constants basically using the PSLQ algorithm. And for that it's very helpful to know basically the values of the multiple polar logarithms to high or arbitrary accuracy. So that's a motivation for that. Now, when we implemented basically the multiple polylogarithms in GiNaC, we not only implemented the functions Li and the functions G, but also a bunch of other functions, Nielsen generalized polylogarithms or harmonic polylogarithms. The only message I want to say here is basically that basically there's a whole slew of functions. Basically, some are more special than other ones, and basically it takes some time to sort it out. And we will see the same pattern basically again if we go to the elliptic case. So don't be worried about having similar functions with different conventions, nomenclature. Basically, this is all very normal. So let me now come to elliptic curves. And basically, what are the functions we want to implement for numerical evaluations? And basically, I would like to spend quite a few slides to explain basically what we need to implement and basically what is known from mathematics. And there will be quite some slides also on modular forms. So, elliptic curve. There are various ways to think about an elliptic curve. One way is basically given by a cubic equation over the complex numbers, and then if you plot just the real slice, it looks a little bit like that, and this goes on to infinity, so there's also a point at infinity there. This is one way, basically, as basically an algebraic curve, basically with a dedicated point, which in that case is the point at infinity. Another point is saying, well, I can write it basically as the complex number modulus a lattice. The lattice is generated by two vectors, which I call psi1 and psi2. And in order to be a non-degenerate lattice, I would like to impose the condition that the imaginary part of this ratio is not equal to 0. And then basically the elliptic curve basically is just, you can, all points on the elliptic curve are just inside this parallelogram here. And then you basically, if you're basically in the next parallelogram, it's just a copy of the old one. So it's periodic, it's double periodic basically with the two lattice vectors. If you go back to the curve, basically, it's always complex numbers for us always. Then you can say, well, it's a complex curve, and you know basically a complex space, you can think about a real space of dimension 2. So then you come to a real Riemann surface. You can also get basically a torus basically here. And you can also think about it if you take this parallelogram and identify that side basically with this side here and that side with that side here. So wrap it up. Basically, you also get to a torus. As I said, basically, an elliptic curve is an algebraic curve of degree 3, and with one special point, which is here at infinity. The special point here is the origin, and here I marked basically one special point there. For me, I find it very convenient to work here with this middle picture, basically C mod a lattice. So basically my information, basically what the elliptic curve is encoded in these two complex numbers, which are basically the periods of the elliptic curve. So these are basically here just these two vectors here. You can also think about basically the integration of some differential form along that cycle and that cycle here. It's exactly the same thing. Now, again, here's my lattice, basically, and let's say it's generated by psi1 and psi2, then it's clear that the same lattice is also generated by different vectors. For instance, okay, I can normalize, first of all, my vectors to 1 and tau, where tau is the ratio of the two vectors. And then basically I can say, okay, it's the same lattice is generated by the vector 1 and tau prime, which is the one here, which gives me here this red parallelogram, and it's exactly the same lattice. So nothing should change. Now, basically, if I change basically the periods, basically by a transformation being a linear combination of the old periods, of course, it only makes sense if basically these are integer numbers here, then it should be invertible. So basically this matrix here basically is an element of this group here, the special linear group over the integers. Okay, so a change of basis if I change my periods, and now translate it basically if I always rescale one period to 1, and I just have one complex parameter tau, basically in terms of tau and tau prime. Tau prime is my transform tau. It's basically this transformation is just basically translates to a transformation for tau in this form. So the next thing, basically, now we go a little bit to modular forms. We can ask basically what are functions which transform nicely under this transformation. So such a transformation is called a modular transformation, and basically the interesting functions are basically which transform according to that law here for basically the elements from this group, and k is an integer and it's called the modular weight here. So this is called the automorphic prefactor here, and basically k gives the modular weight. So, and then basically, okay, tau, we can, without loss of generality, assume basically that it's always in the complex upper half plane, and then basically a meromorphic function from the complex upper half plane to C is called a modular form if transforms like that. It's holomorphic on H, and it's holomorphic at I infinity. That's the cusp, basically. So that's the definition what a modular form is. It has these three properties here. Now, that is a modular form for the full modular group SL2Z. In addition, basically, there are subgroups of this group here, which basically are standard. So basically, they are called congruent subgroups, and they are defined here. Basically, gamma 0 of n is basically the requirement that this coefficient is a multiple of big N. And as you go down here, you have more and more conditions there. In order to define basically modular forms for these subgroups, basically, again, you require nice transformation properties, but now only for transformation from this subgroup, plus holomorphicity on H and at the cusps. So these basically groups, they might have more cusps, not just at I infinity. Now, a few technical details. In the end, basically, we want to implement basically modular forms in GiNaC. We need something which is called a Dirichlet character. I tell you in a second why we need that, basically. It's a function from the integers, basically, which has basically is periodic with big N, and N is called the modulus of this character. It's 0, basically, if small n and big N have a common divisor, and it's unequal 0 if this is not the case. And then it has this factorization property. So we have here basically the modulus of the character, and then there's something like the conductor. Basically, it's defined here by this condition there. It's basically the smallest positive divisor, such that basically there's another character modulo D, which fulfills this property here. So a character where the conductor equals the modulus is called a primative character. That one is which we will use in the sequel. So we need primative characters, which simply means conductor equals the modulus. Okay, so these are abstract properties. So basically, actually takes so basically on two integers, it's a way. And basically, if n has a factorization where basically this u is either 1 or -1, so a unit, then the prime factorization, basically, it fulfills this property, and then the individual Kronecker symbols for a unit or for two or odd primes, they are defined separately, and the definition I didn't give here. You can look them up in the book. Mathematician will know them. These are not too complicated. What is important, basically, is the message that whenever this A is something mathematicians call a discriminant of a quadratic field, then this Kronecker symbol is a primitive Dirichlet character with conductor given by the absolute value of A. So the possible values for which you get a primitive characters, the first ones I've listed down here. So why do we need characters? Well, first thing we can do, what mathematicians do, they relax a little bit the transformation law, that we can define modular forms with character, where basically, apart from this automorphic factor, you also get the character of this parameter here in front. Okay, that's a nice thing to do. Why would you do that? It's because then you can give very explicitly basically what the space of modular forms for the concurrent subgroup gamma 1 of n is. It basically decomposes basically into a space of modular forms with characters. I should say the modular form for a given concurrent subgroup from a vector space. It's a finite dimensional vector space. It splits basically in a vector space for cusp forms and the complement, which is called the Eisenstein subspace. And basically this Eisenstein subspace, we can give very explicitly. So the vector space here, the Eisenstein subspace of these ones, basically describes them very well. And that comes basically on the next transparency. Basically, I recall that we have this Dirichlet character whenever that is a discriminant of a quadratic field, basically defines a primitive Dirichlet character. And then we define basically a quantity basically by its Q expansion, and Q bar is basically here for me always e to the power 2 pi I tau. Here you see basically two characters, two Dirichlet characters, and the sum is overall divisors of n, and that's basically a Q expansion. And then all what you need for this Eisenstein space with characters is basically these formulas, basically, where you basically say, okay, apart from tau, you also allow k tau, multiple of tau, integer multiple of tau, which means Q bar is raised to the power k. And then you can say, okay, if you don't have this k here, so let me say on what it depends. So this little k is a modular weight. A and b basically are integers, which are discriminants of quadratic fields, and k is basically the factor in front of this tau. So for modular weight, basically not equal to 2, and basically not having the trivial characters, basically this defines basically a modular form with characters. In modular weight 2 and basically A and B corresponding to the trivial character, one defines it in such a way, then again, it's basically a modular form. So with that, basically, and basically this formula, it's very important, basically, since you can code out very easily the Q bar expansion of modular forms. Basically, it's given by this formula here. And having modular forms, basically, you can define iterated integrals of modular forms in the same way as we define iterated integrals as usual. I should say, basically, the integral over a modular form is in general not a modular form. There's no reason to be the case. In the same way as an integral over a rational function is in general not a rational function. Maybe if we now look at the full modular group, basically we have a cusp at tau equals I infinity. And I just told you that basically by definition, modular forms are holomorphic at the cusp. So they have a Q bar expansion of falling 4. Now what we actually usually do, we don't integrate over tau, but we change to Q bar. Then basically, if I write down basically the Q bar expansion for this expression here, you see it reads like that. So whenever is non-vanishing at the cusp, basically if you change the variables to Q bar, you have a simple pole at Q bar equals 0. So the cusp at tau infinity under this identification here is mapped to Q bar equals 0. But we have a simple pole there. Now, why did I tell you so much about modular forms? It's because, for me, the most elegant solution of the equal mass sunrise integral and other quantities can be written as iterated integrals of modular forms. So we would like to evaluate these integrals at some point numerically. So in addition, basically, the title is elliptic polylogarithms, and it was already several times mentioned, basically, that there are several definitions of elliptic multiple polylogarithms. So let me basically go a little bit in this field. So the first thing is basically you start with Jacobi zeta function. There are various definitions which differ basically. Do you take Q, which is e to the I pi tau, or Q bar, which has a factor of 2 there? Do you include a factor of pi there? So I've picked here basically the definition from the Institute of Standard and Technology. So the first zeta function is defined like that. And then you can define the Kronecker function. So in my definitions, then some factors of pi appear here, but more or less it's basically the same as we saw in previous talks in this conference. And what is important of us is not really this Kronecker function here, but the expansion in one variable. Symmetric in Z and alpha, you expand it in one variable, let's say we expand it in alpha, and then we get the coefficients, which are then only function of 2 variables, Z and tau, and these basically are the function which we are interested in. So basically, they have nice properties. They have only simple poles as a function of Z. They are almost periodic. They are periodic by 1, but quasi-periodic by tau. And they are almost modular. And it's just, you can express this function in terms of Eisenstein series, and just the Eisenstein series of weight 1 basically spoils the really nice transformation properties. So this is basically as good as we reasonably might expect things to be. That basically is the question, if you would like to define elliptic multiple polylogarithms, basically, you might say naively, I would like to have things as good as possible. For instance, you would like to have integration kernels, which are on the one hand double periodic, which are basically meromorphic and only have simple poles. And Federico Zerbini nicely explained that yesterday. The upshot is that is not possible. So we cannot have the full cake and eat it. You have to give up basically one condition. Then basically, if we look at Feynman integrals, basically what we would like to keep is basically the properties of meromorphic and only simple poles. So we give up basically the property to be double periodic. So we say, okay, we know that as a logarithm, if you go around basically 0, you don't end up with the same value. So instead of a single valued function, you think either of a multi-valued function, or you think about a function defined on some covering space. That's not a problem for us. And with that, basically, we can define basically iterated integrals according to these coefficients from the Kronecker function, basically, and we just iterate and iterate again by integrations in Z. Let me note, basically, that this integration here assumes that the parameter tau is kept constant, basically, in all expressions here. So you have a fixed elliptic curve, and you integrate in some variables Z. So this is one version how you can define elliptic polylogarithms, and they are called the gamma tilde functions. Now let me also say a little bit about moduli spaces. We know moduli spaces already from the multiple polylogarithms, where you think about basically the moduli space of marked points on a Riemann sphere. That is basically this situation here. And basically, it will be basically marked points of a genus 0 curve. Now, if you go to genus 1, basically, we might consider basically the modulus space of basically marked points on a torus, or here basically in the algebraic thing, marked points on an elliptic curve, or an algebraic curve of genus 1. Now, what we should look at is basically what are standard coordinates for these moduli spaces. Now, basically in genus 0, we know the dimension of the modulus space of n points on a Riemann sphere is n minus 3. Why n minus 3? It's because you can use Möbius transformation to fix 3 points at prefixed values. So usually you fix 1 point at 0, another one at 1, and the other one at infinity. And then there are n minus 3 points free, which can be wherever they want. So basically your standard coordinates at genus 0s is basically just a bunch of set coordinates, n minus 3 set coordinates, and that's it. The situation is a little bit different at genus 1. So the dimension of the modulus space of n marked points on the genus 1 curve is n. But now you have to think a little bit, basically, what are my standard coordinates? Again, you can use translation invariance to fix basically 1 point at 0. So then basically you have n minus 1 points remain. And the last coordinate is basically this parameter tau we had before, which describes basically the shape of the torus, if it's thick or thin. A sphere has a unique shape. It always looks like a sphere. So basically the situation is here different at genus 1. Basically the natural coordinates basically are n minus 1 punctures and basically tau. And that is very good actually, because we've seen that in the equal mass sunrise, the most elegant formulation is iterated integrals in tau or q bar, as you like. And then basically now, if you go basically to more complicated Feynman integrals, and you could go to the unequal mass sunrise integral, you basically end up basically with a geometric object, which is M13, basically the modulus space of 3 marked points on the genus 1 curve. And then you have basic coordinates tau, Z1, Z2. So that means basically, if you now look basically at the differential equations for these Feynman integrals, you can think what is the derivative with respect to tau, what it is with respect to Z1, what it is with respect to Z2. And then you can integrate the differential equations. And then basically, if you decide to integrate in some Z variables, you get the gamma tilde functions as before. But you're not forced to do that. You can also decide to integrate in tau, basically, and then you get basically something which has a smooth, nice limit with the equal mass sunrise. Both things are possible, and it's completely up to you what you would like to use. So, some more definitions. Basically, that is basically a relic from some previous work. Basically, when we looked at the equal mass sunrise, we realized very early on that we can write down an all order epsilon solution, basically order by order in epsilon, in terms of certain functions, basically, which we called ELI, which are just basically a product of 2 classical polylogarithms coupled together by this variable q, basically. It's very symmetric, so as a physicist, we like that. And then basically, building out from that functions, we defined linear combinations, basically, which are defined here, which we call then the E-bar functions. So basically, they appeared first, basically, in the all order epsilon solution for equal mass sunrise. And they are for other things. For instance, they are useful to expand basically the coefficients we get from the Kronecker functions in the variable q bar. They are given in terms of this. And basically here, basically q bar expansion is immediately given there. So basically also here, the q bar expansions basically is rather simple. So the last I would like to mention that some people who are also here in this conference figured out that basically many Feynman integrals, which are elliptic, can be written in the form that basically you have one final integration, which is basically not in the class of multiple polylogarithms, but all inner integrations, basically they are like polylogarithms. So they have integrals like that, here multiple polylogarithms, and then integrated of something which is non-polylogarithmic. Typical example is the square root of a fourth order polynomial. So that basically also exists as a definition basically of elliptic polylogarithms, and it's clearly also related to the Feynman integrals we look at. So that was basically something basically which exists. And now let me outline a little bit what we implement in GiNaC, basically how we do that. So we talked about how general can we be, and basically what we actually do basically all the time, we would like to evaluate iterated integrals. Basically, we have some differential one forms, which we pull back to a line segment, and then we integrate along this line segment in this way here. And the only difference is basically what are these differential forms. One more thing, basically, we can basically evaluate this integral by series expansion. Basically, whenever basically these differential forms or these functions f I had just before basically are holomorphic in some domain up to a certain basically lambda 0, basically that might be where the next pole is. And what we also allow in addition basically is that basically at basically z equals 0, we allow a simple pole. That situation we already have for the multiple polylogarithms. These are exactly our trailing zeros, and the whole story translates to every function, which is a little bit more complicated, which we would like to consider. So basically, we assume that basically in a neighborhood basically of the origin, basically our function is holomorphic and has basically has a Laurent expansion basically in Z with at most a simple pole at the origin. If it has a simple pole at the origin, we say it's a trailing zero. Now the trailing zero basically we can handle in exactly the same way as we do it for the multiple polylogarithms. We use basically tangential base point or shuffle product regularization to basically to produce explicit factors of some logarithms, and then the rest is regular. And that is exactly the same as in the case of multiple polylogarithms. So now, basically, what can you expect in the future in GiNaC? Basically, as I said, basically, we define a general class for iterated integrals, and then it only matters basically what you say, what are your integration kernels. And here I've listed basically integrations kernels which basically pop up in physics. So the first ones, they are related to the coefficients of the Kronecker functions. So these ones here. And as I said, basically, these integration kernels you can integrate in two directions. You can either integrate it in Z, basically, then you get the gamma tilde elliptic polylogarithms. So basically, in that case, you would say it's basically this kernel here, and basically there's a shift Z minus Zj, and basically K refers to this index here, and then it obviously depends on tau. Or you can integrate it basically in tau, then the other parameters basically are, again, the index K, and then basically the value of Z here. So these are the two versions basically related to the coefficients of the Kronecker function. Then basically we have basically all the stuff which are modular forms. So the first thing which we implemented is basically the Eisenstein kernels, depending basically on three integers. K is a modular weight, A and B are integers, which are basically discriminants of quadratic fields and define basically the Dirichlet characters, which enter basically the definition of this generalized Eisenstein series. And K is basically this factor basically which multiplies tau. So this defines just the Eisenstein kernels. But then we see basically, this is almost sufficient what we need basically, because anything else basically what pops up basically is usually just basically a polynomial in these Eisenstein kernels. So we also provide then basically integration kernels which take a polynomial in these guys. This polynomial should be homogeneous of modular weight. So the modular weight is basically this k here. And this q bar is then a dummy variable which tells me I have to expand this polynomial in q bar to basically get my series expansion. Then we implemented basically the ELI functions. Okay, the parameters are obvious. They are exactly the ones which are basically appear in the definition there. And finally, basically, for these people who basically think, okay, I want really a special thing like a 1 over square root of a fourth order polynomial, you can basically define f to be basically this function, f1 over square root of a fourth order polynomial in the variable y, and then basically the program basically calculates the series expansion for that, provided it has at worst the simple pole at the origin and has a convergent Laurent expansion in some domain, and then you can also use that. So that should cover a very wide range, basically, what basically people might want to use. And then basically we thought we do it basically as similar as it was done basically for the multiple polylogarithms. And here's basically one example, basically how it would work. It's a snippet of a C++ code. You can define basically how many digits you want. And basically, okay, here down I have iterated integrals. I define some values for tau. Then I define basically what q bar is just by this expression here. I have a set variable, which I set to 0.9. And then basically I say, okay, I have two integration kernels, which I take basically as the coefficients of the Kronecker function. Basically, I would like to integrate in tau. So, and then basically this one is G2, this one is G3. So I give these parameters here. And then they also depend on a set, basically, which I defined up there. And that's it. And then instead of G, basically now the general thing is called simply iterated integral. It takes a list of integration kernels, which is then basically just a list of what you defined up here. And then basically, if you integrate in tau, basically de facto you integrate in q bar. So that's why a q bar enters here. Basically, you integrate up to this value here. And then you just say, okay, give me the number out of it. So evaluate to a floating point number. And then you get basically the 50 digits basically here. That thing is, of course, real, but basically q basically is a complex number. So you expect basically some small imaginary parts, which is orders of magnitude smaller than that. Actually, I mean, it should be 0, but since you calculate to finer precision, this is harmless. So that's the way basically it will work. And that basically already brings me to my end of my talk. Let me remind you that basically in the end, physics, we always want a number. We want to compare to experiments. And it's a special case of these transcendental functions we care about basically. It's a nice thing to be able to evaluate them with arbitrary precision. For instance, it's very helpful for the PSLQ algorithm. And basically, I've given you basically a flavor what will be basically quite soon coming in GiNaC. And with that, basically, I'm finished. Thank you for your attention.
Thank you very much. And let's take a quick second to unmute ourselves. And I see already a question by David.
Yes, my question concerns the use of Atkin-Lehner transformations to optimize convergence by making Q as small as possible. On your transparency, you put Q equals 10i, that's no problem. You go to tau equals 10i, you go near tau equals 0 and you'd have problems. Now, in the case of the equal mass sunrise diagram, I showed very explicitly how to transform between cusps so that you always have for any kinematic variable good convergence. Have you implemented such facilities in GiNaC?
At the moment, not, basically. We are still considering that, and we have to see basically what really needs to be done. Our approach here is basically to have basically a wide variety of different functions which work all the same. So basically, to your specific question, basically, you can basically, if you think how I would use basically this package, then I would integrate a differential equation. I can integrate it from different starting points. And in that case, basically, I can always assure basically that I get basically a Q bar small enough. It has to be discussed basically how complicated that thing is in full generality. It has to be a code which is also maintainable, and basically, yeah, I have to see basically.
But you know from your own experience on the examples that I gave you for the electron propagator, and I know from Claude Dawes' recent talks that this can be really, really useful if you're in a kinematical regime in which the Q that you happen to choose is not small. There are well-defined transformations on the upper half plane to getting you.
Yes. The point is basically, what is basically the amount of work basically to have it in full generality compared to the profit you get, basically.
Well, the profit can be huge.
The profit can be huge, but basically
the work is large.
The restriction is that basically people then, as soon as it is public available, people use it in all situations. So it must be foolproof, basically, and must work in every situation. So we are still a little bit undecided, basically, what to do there, basically, how far we can go.
Thank you.
So the next one was Francesco.
Yeah, so thanks for the nice talk. So you mentioned a few slides before that now GiNaC also allows to use basically user-defined functions, so of the form f of x and y, so very general integration kernels. So I was wondering if you could elaborate briefly on how the expansion is done in that case. So if it still uses some sort of Q series or something else?
No. I should say, basically, you can expect this thing to be slower than the other ones.
Yeah.
I spent quite some time basically on these Dirichlet characters because these can be computed very fast. So the Q bar expansion of this modular forms is very fast. And I can also say, basically, if you integrate these G functions from the Kronecker thing, basically, if you what the expansions are in tau, what the expansions are in Z. Basically, this expansion in tau is also fast, and the expansion in Z. And the most general thing is obviously the slowest one. Why is it slow? Because we rely on the general series expansion methods of GiNaC there. So it will simply expand it basically to sufficient high, basically order, and simply takes that. So this is basically it's completely arbitrary user-defined functions. We don't know anything about that. So we cannot put any optimization for that. So, and that means basically it will be not so fast as the other ones.
Yeah. Thank you.
Next was Vasily.
Hi, my question is actually also related to the questions which have been asked previously. It's also regarding the evaluation of iterated integrals here. So in both cases of the integrals over the kernels which you defined, and in a general case, can it happen that for some inputs, the series will not actually converge? What I mean is that, do you actually make sure that the point which you choose to expand your kernels includes, so the radius on convergence around this point actually always is inside the region which is required for the any inputs pretty much.
Again, basically, if you really would allow user-defined functions, then you have to shift this responsibility to the user. In full generality, I cannot guarantee that. Basically, that's the thing is. And basically, it will work basically that basically whenever this condition here is satisfied, basically, then basically it's guaranteed to converge. Of course, if you come close to the boundary, basically, then it will be slower. So it will be something which is a responsibility given to the user of these functions. So we still discuss basically in which special cases we know transformations to make it faster, but in full generality, basically, it will not be possible. Of course, some of the subsets of the functions I discussed, I know some transformations. The question is basically, do we implement them immediately or in a second stage? That's important for us.
And did you think of doing something similar to what actually Francesco was, of how Francesco, for example, was approaching to solving the differential equations, in a sense that trying to expand the kernels about different points and somehow combine them for in the iterated integrals. So did you consider that strategy also?
No, basically, because basically it should be a tool basically which is, I mean, you're referring solving numerically the differential equation for Feynman integrals, I assume.
Well, I mean doing something similar, but such that it actually works for the iterated integrals. I assume something similar can be done, right?
That is probably yes. I think there's also a talk with a similar topic tomorrow by Robin Mazurka. It's the same title, maybe. Yeah.
Okay. Are there further questions?
Can I ask another question, actually?
Sure.
Sure.
Yeah, I mean, it's just a simple question. Do you have any timeline for when this implementation will be available publicly?
I think it's a matter of weeks.
Ah, so it's very soon. Okay.
Yeah, of course. Yes.
Okay. Thanks.
Further questions? Okay, if not, then let's close this session. And I hope to see all of you for the conference dinner tonight in 1 hour. And again, tomorrow morning for the discussion session based on the topics of today's talks, starting at 11, both in this Zoom room. So hope to see all of you there. And thanks again to Stefan.